Most current encryption methods rely on the fact that classical computers would take centuries to solve certain mathematical problems. Quantum computers do not work linearly. They use quantum bits to perform these calculations in a fraction of the time, making current cryptographic standards vulnerable to near-instant decryption. To counter this, the Department of Science and Technology launched the National Quantum Mission. The goal was to build a defense layer based on the laws of physics, specifically quantum mechanics, which cannot be bypassed by raw computing power. This mission has now produced a concrete result: the successful demonstration of an operational 1,000-kilometer quantum communication network. Maintaining a quantum signal over 1,000 kilometers is an extreme hurdle. Physical distance is the primary threat to quantum stability. Originally projected at 8 years for 2,000 kilometers, hitting the 1,000-kilometer mark in less than 2 years heavily outpaces the mission's initial schedule. This achievement moves the technology beyond controlled laboratory settings. It is a live deployment, tested in real-world conditions rather than a simulated environment. The physical layer of this network uses standard optical fiber. The hardware must be capable of transmitting and receiving discrete quantum states through the same glass cables that carry conventional internet traffic. To understand how this scaling happened so quickly, we will deconstruct the ARMOS hardware nodes, examine the network's error rates under load, and analyze the financial architecture used to capitalize the domestic startup ecosystem. This milestone represents the first instance of quantum-safe encryption operating as a functional layer of India's national digital infrastructure. The network's core hardware is indigenous, developed by the deep tech startup QNew Labs under the support of the National Quantum Mission. The specific system architecture used is the ARMOS Quantum Key Distribution Platform. This QKD system uses the principles of quantum mechanics to distribute encryption keys. It sends single photons between nodes. Because these photons exist in a quantum state, any attempt to observe or intercept them will change their properties and alert the system. However, photons traveling through fiber optic glass naturally degrade. Over long distances, the signal becomes too weak to be read accurately. In classical networking, engineers use amplifiers to boost the signal. But in quantum networking, the no-cloning theorem states that you cannot amplify a quantum signal without destroying the information it carries. The ARMOS system addresses this by generating secure keys over links as long as 200 kilometers without any signal amplification. These 200-kilometer jumps act as the building blocks for the broader grid, allowing engineers to chain multiple nodes together to cover a 1,000-kilometer path. Because each link can span 200 kilometers unamplified, a 1,000-kilometer network requires only 4 intermediate relay nodes, a hardware efficiency that makes a national-scale deployment logistically feasible. Physical distance is only half the challenge. For a quantum network to be practical, it must share existing fiber optic cables with the massive volumes of traditional internet traffic already in place. Inside a commercial fiber cable, the environment is crowded. Traditional data pulses move at high power, creating noise that can interfere with delicate quantum signals. To test its resilience, the network was operated alongside a 10 gigabit per second stream of classical data traffic. The key metric for measuring performance in this environment is the quantum bit error rate, or QBER. QBER is a sensitive security tripwire. If an intruder attempts to tap the fiber, or if classical data noise disrupts the photons, the error rate will immediately increase, signaling that the key is no longer secure. This diagram shows the coexistence challenge, keeping the discrete, low-power quantum key pulses stable while high-volume classical traffic flows through the same fiber. During the demonstration, the network successfully maintained a QBER of less than 4%. A QBER below 4% is a critical benchmark. It proves the system can distinguish between background noise and an actual interception attempt, ensuring security without generating false alarms. Maintaining these metrics alongside 10 gigabits of traffic demonstrates that the network is stable enough for high-volume commercial implementation. The speed of this deployment was driven by the mission's financial structure, which is backed by a 6,003 crore rupee budget allocated through 2031. To accelerate development, the mission uses a hub-spoke spike model. It divides research into 4 thematic hubs at top-tier institutions, focusing on computing, sensing, materials, and communication. IIT Madras leads the communication hub responsible for this 1,000-kilometer network, working in coordination with the Center for Development of Telematics. By centering these hubs at existing engineering campuses like IIT Delhi, the mission leverages lab infrastructure to compress the time from concept to prototype. Beyond the labs, the mission supports 17 domestic startups managed through the Technology Development Board and BIRAC. The government has introduced flexible financial instruments to fund these companies, most notably optionally convertible debt. Deep tech development requires significant capital before a product is ready for the market. Optionally convertible debt provides these startups with funding for hardware and R&D without requiring the founders to give up equity in the earliest, most vulnerable stages. This funding model has already allowed the mission to expand its reach to 9 additional startups specializing in fields like atomic memory and quantum biosensors. The 1,000-kilometer milestone was reached by treating quantum research as a heavily capitalized industrial pipeline rather than a purely academic exercise. With the 1,000-kilometer demonstration complete, the first operational endpoints are now being integrated into the network. Defense is the primary beneficiary. This level of encryption is being deployed to secure command and control communications, ensuring that strategic data remains unreadable to any outside entity. The security layer is also being extended to financial data centers and the management systems for national power and water infrastructure. The ARMOS hardware is designed for resilience, built to operate in environments that go beyond standard urban data centers. This includes the maritime domain, where quantum communication technologies can be used to secure data transmitted via underwater links. Future applications will see these QKD networks integrated directly into deep-sea cables and hardened underground bunkers. This infrastructure is a dual-use asset. It protects classified government data while providing the security foundation needed for the broader civilian digital economy. From a geopolitical standpoint, any nation that relies on foreign-made quantum security hardware creates a permanent dependency on external technology providers for its most sensitive data. As the timeline for quantum computers capable of breaking current RSA encryption continues to shorten, the urgency to deploy domestic, quantum-safe hardware has become a national security priority. By developing and deploying this 1,000-kilometer network using indigenous hardware and local financing, India has established a baseline for secure communication that remains operational against future decryption threats without relying on foreign technology.